Based on our previous activity in StatCrunch, we saw that if p was 0.5, the sampling distribution of p hat had these three characteristics. The mean was the mean of the sample proportions was 0.5, the population mean. It was unimodal and symmetric, approximately normal in shape, and we noticed also that the spread would decrease as the sample size increased. But what happens if the mean is not at 0.5? Does that make a difference? We're going to examine that by looking at another little applet called the Reeses Pieces applet. And I want to look at what this does. I'm going to change this to 0.45 because we already did 0.5, so 0.45. And we're going to do a sample of 25 candies, and I want to look at the proportion of orange candies. So we're saying the proportion of orange in the population is 45%. So if I draw a sample of 25 candies from this machine, I think it's really cool how that does, I got a sample with 36% orange, and it plotted a dot right here at 36%. Kind of hard for the screen, so I'm going to cover up where it says Reese's Piece, and I don't really need that part. Now, if I do a second sample, notice the second sample has a different proportion of orange. Now it has 52%, so it plots the sample proportion down here. I can do again. Another 36. Now, if I want to do maybe about 50 samples, and I'm going to turn off animate so it just does it really quickly. Okay, all of these dots here then represent sample proportions. The most recent was 44%, so that represents the dot right, let's see, I think in this stack, probably right there. The top of that stack, that would be the 44%. So if we look at our notes, I want to just have you write down a few things. So let me get rid of this here. So if we look at what all of these things represent, this is the population of candy. Each member of this population is an individual candy piece, and it has a distribution of 45% orange and 55% not orange. This is a sample from this population. In the sample, each individual is one piece of candy again. This has a distribution where p hat is 0.36 orange, and then there are 0.64 not orange. Down here is what's called a sampling distribution of p hat. Each individual dot in this distribution is not an individual piece of candy. It is the proportion of orange in one sample. So this represents 50 different samples from this machine. The most recent sample is 36%. That represents the dot right here. Now, let's then look at what happens if we change the sample proportion to be something other than 45%. How does that affect the distribution? So I want to go ahead, first of all, and do about 400 samples. Okay? We notice here we have a fairly unimodal and symmetric distribution still. We notice the tail maybe is slightly longer on the right-hand side. What if we made this a lot smaller? What if we made this 0.1 and did 400 samples? What if we did another group of samples? Notice here we have a unimodal distribution, but it's skewed to the right. What if we made the probability a lot bigger? Draw some more samples. Notice we have something that is skewed to the left. So it looks like we can't always think of a distribution of a sample proportion as being unimodal and symmetric. It's unimodal, but not always symmetric. We seem to see a lack of symmetry when we are at a very high or a very low probability, close to 0 or close to 100%. Now, we can see this in another place. To pause a moment here. We see here, this is not a distribution of p hat. This is a distribution of a binomial variable. So this would be a situation where the probability of success is 0.5. We do 10 trials. So the expected number of successes would be 50% of 10, or about 5. So we see that we're centered at 5. Sometimes we get more than 5 successes, sometimes less, but it's very unlikely to get 10 successes when the probability of success is 0.5, or 0. Now this turns out to have the very same shape as a distribution of sample proportions, because if I take the number of successes divided by the number of trials, I'll get the proportion of successes. And so that it will have, this will be 0.5 instead of 5, but the shape will be the same. So all the things I'm doing here apply to sample proportions as well as counts. If I were to move the probability up higher and higher, notice how much more skewed the distribution becomes. But what if we change the sample size? Okay, so if I have a very skewed distribution, but I make the sample size very big, notice that it becomes approximately normal, except for this really long skinny tail, but there is so little data in that tail that we can almost think of this as an approximately normal distribution. Likewise, if I move it over far to the left, it's going to have the same thing. If I have a small number of trials, it'll be very skewed to the right, but a large number of trials, it becomes approximately normal. It turns out there is a rule of thumb for this. And the rule of thumb is this. First of all, what affects the shape of the distribution? The population proportion. If p is closer to 0% or 100%, the distribution becomes more skewed, but increasing the sample size n makes the distribution more symmetric. The rule for this is that if NP, the sample size times the population proportion, is greater than or equal to 10, n times the 1 minus p, both are greater than or equal to 10, then we can say the distribution is approximately normal. So if we go back to what we were looking at, let's examine this. Here, if we have a probability of 0.1, we would need to make this 10, we would need a sample size of approximately 100 in order for 0.1 times 100 to be greater than or equal to 10. Now, if we went to 90%, we would need, we would say, well, 0.9 times 100 is 90, that's more than enough. But remember, that would be p times n. I also need 1 minus p times n to be greater than or equal to 10. So I'd also have to say 0.1 times 100 for this one. Now, if I go down to a smaller, let's go to like 70%, I don't need 100. I would just need maybe 70 now, because 70 times, no, actually 0.7 times what is equal to 10? 0.7 times 70% of, I'm not doing very well. I'm not doing this off the top of my head. But 70% of a smaller, this would actually be, actually let me go down to 30%. That would be easier to do it this way. Sorry. 30% of 0.3 times maybe about 35-ish. Because if I do 0.3 times 40, that's 100, and that would be 12. So I could go even a little bit smaller than that, and I'd have a fairly normal distribution. Now, if I go up to 5%, 50%, I would only need a sample size of 20 to get that required 10. So a bigger, the closer the probability is to 50%, the smaller the sample size is needed to get something that looks approximately normal. If I have a very high or low probability, then I'm going to need a larger sample size to get something that looks approximately normal. And the next video explains the math behind this, so I won't go into that, but you can you can see why specifically do we use 10 for this rule. But the big idea so far is both the population proportion and the sample size affect the shape of the distribution of p hat.